Hello there, welcome to Chemistry Chapter 2, Lecture 2. In this lecture we're going to cover On Your Own Problems 2.6 through 2.8. In the book we're going to be going through page 50 to 59. And before I get started, I just want to invite you to like, comment, and subscribe. And you can support my channel by clicking on a link in the description box and give a small donation. Or you can scan this QR code and it'll take you to my Ko-fi page. Thank you so much for considering that. So in this lecture you will need your notes and your calculator. So one of the things that we talked about in lecture number 1 was this equation Q is equal to MC delta T, where Q is equal to heat absorbed or released. Okay, so if it absorbs, the object gets hotter. If it's released, the object gets colder. M is the mass, and it's usually going to be in grams. So Q would be in joules. Mass is in grams. C is the specific heat. You do need to memorize this equation. The units for that is joules divided by grams times degrees Celsius. And then delta T is equal to the final temperature, so we're going to call that T sub F, minus the initial temperature. So the object started at an initial temperature, and most of the time it heats up to a final temperature. Of course, sometimes it cools down, and so then in that case the initial temperature is higher than the final temperature. Okay, so let's use this equation in On Your Own 2.6. So that's on page 53. All right, this problem says a 502 gram iron rod is heated to an unknown initial temperature. If while cooling down to a temperature of 22 degrees, the rod releases 597.5 joules of energy, what was the initial temperature? And our hint is when an object loses energy, its Q is negative. All right, so this is a good exercise. All right, so we are on page 53 here. So let's write down what we know about the problem. So we know that Q, it says it releases 597.5 joules. So it's negative 597.5 joules. All right, we also know the mass. That's 502 grams. The specific heat we know because it is iron, and if you'll flip back to page 50, you see that iron has a specific heat of 0.4521 joules divided by grams times degrees Celsius. All right, and then we have a final temperature. So T sub F, a final temperature of 22 degrees C, because it cools down to that temperature. And we want to know what is the initial temperature. Now another equation that we need to think about is delta T is equal to T final minus T initial. So I've written that again. I wrote it up here. Okay, so we have Q is equal to MC delta T. Let's fill the numbers in. Q is negative 597.5. That's equal to 502 grams times specific heat 0.4521. And then I'm going to solve for delta T, and then I'll figure out that initial temperature by plugging the numbers that I know about temperature in. So in order to solve for delta T, think about it algebraically. You're going to pull this 502 times 0.4521, pull it underneath the negative 597.5. That's just dividing by both sides by 502 times 0.4521. So we'd have negative 597.5 joules divided by 502 grams times 0.4521 joules over gram times degree C. Okay, so let me show you how to put this in your calculator so as not to make a mistake here. Okay, you've got negative 597.5 on top. Divide that by. What you want to do, you're not going to put it in your calculator exactly like this. Put a left parenthesis and then do 502 times 0.4521 and then hit the right parenthesis. That'll get your order of operations right. So you have a delta T of negative 2.63 degrees C. That means the object cooled down 2.63 degrees. So now we're going to use delta T is equal to T final, which minus T initial. Now we know T final. We know delta T. It's negative 2.63 is equal to 22 degrees C. That's from the problem. Minus T initial. So what we want to do is bring that T initial over to the left. That makes it positive. Bring that T initial over to the left. You can change the sign and then add 2.63 to both sides. Okay, so that would be 22 degrees C plus 2.63 degrees C. So our initial temperature would be 24.63 degrees Celsius. All right, so we added our initial temperature to both sides, and then we added 2.63 to both sides. But I like to think of it as I want to change the sign to a positive T sub I, so I pull it to the other side of the equals. That makes it positive. And then I add 2.63 degrees Celsius. So if I push that to the right side of the equal sign, it makes it positive like this. And then you can always check. Just plug your numbers back in and see if you get what you're supposed to get. So 22 minus 24.63 gives you negative 2.63. So you can always check your answer on these. All right, so that's a good one to start off with. Probably that one was a little more complicated than this next one. So on your own 2.7 on page 53. So let's bring that into view. That one says if a 15.6 gram object requires 836.8 joules of heat to raise its temperature by 21 degrees C, what is the specific heat of the object? All right, so what do we know? We know that the Q, that heat, is 836.8 joules. We know it's positive because the temperature is getting bigger, so it's absorbing the heat. Our mass is 15.6 grams, right from the problem. Specific heat, we don't know. We want to know that. And delta T is 21 degrees C. So we don't have to figure out the initial and the final and all that. They gave us what delta T is. So that's pretty nice. So if we have Q is equal to MC delta T, that's going to be 836.8 joules is equal to 15.6 grams. We're solving for C, and then delta T is 21 degrees C. So to solve for C, I'm just going to bring the 15.6 times 21 underneath 836.8. So you'd have 15.6 grams times 21 degrees C. And you know the unit, this is the unit, you haven't gotten this equation backwards, because on top the unit for specific heat is joules divided by grams times degrees Celsius, and that's exactly what you're going to have here, joules over grams times degrees Celsius. So you can always check your units if you're unsure. All right, so let's plug this in the way I showed you. 836.8 divided by, left parenthesis, 15.6 times 21, and then close that parenthesis. And you've got 2.55 joules per grams times degrees C. All right, so these are good algebra problems. Okay, so I'm going to, instead of stopping here, what I'd like to do is introduce you. You don't have any of these on your homework, but I want to introduce you to the calorimeter equation. So you're going to want to read in your book. So we're going to do two calorimeter problems on the next lecture. But let's talk about what a calorimeter is. So if you'll look at page 54 in your book, and you'll be doing a lab on this. A calorimeter is, just think of this as an insulating material, like styrofoam. The ones in the lab are made of styrofoam. And you fill that with a certain amount of water. And then you have an object. In your lab, it'll be a metal bolt. And you heat up that object. Okay? In the lab, you'll heat it up to 100 degrees C by boiling it. So you'll heat up that object. You're going to know the initial temperature of the water, okay, because you're going to put a thermometer in it. And then you drop that hot object into the water. Well, let's say the water started off at 22 degrees Celsius, okay? That's generally room temperature, okay? And you drop in a hot piece of metal. What's going to happen to the water in the calorimeter? You know, drop that hot piece of metal in, it's going to go psh, right? Well, the water in the insulated material, in the calorimeter, the water is going to rise. Now, it depends on how much water there is and how big the object is, but let's say it rose 2 degrees from 22 to 24. You can gain a lot of information about that object just by knowing how much it raised the temperature of the water. Okay, so that's called a calorimeter. That's how these calorimeters are used for a lot of things in science, but it's how they figure out how many calories are in foods. Right? They do a calorimetry experiment. So the calorimeter equation is right here. We're going to work one problem. So a calorimeter is an insulating device. It's filled with water, used to determine the specific heat of an object. So here's the calorimeter equation. So it's minus Q of the object minus Q of the object, so that's like the piece of metal, right, is equal to the Q of the water plus the Q of the calorimeter. So that means, I explain it in the notes, the heat lost by the object because you put it in water is equal to the heat gained by the water plus the heat gained by the calorimeter. Okay? So, let's work one of these. If you'll open up to, and there's good examples in blue, so you should consider reading example 2.4 in your book on page 55 and example 2.5 on page 56 and 57. That'll help you. It'll help you understand these a great deal, but I'm going to go ahead So this is the most complicated problem that we've done yet. But my experience is that after you work a few of these, students get really good at them. So we're going to do on your own 2.8 at the bottom of page 59. Okay, it says a calorimeter holds 175 grams of water at an initial temperature of 25.3 degrees Celsius. A 54.3 gram piece of metal at 100 degrees Celsius is dropped into the calorimeter and the final temperature of the water is 27.1 degrees Celsius. What is the specific heat of the metal? And we get to ignore the calorimeter in this problem. Okay, so in this problem, we just get to ignore the calorimeter. You don't get to always do that, and we're going to work a couple on the next lecture where you don't. So what you want to do, you can figure out the Q of the water. We have everything we need to know for that. We can't figure out the Q of the object because we don't know the specific heat of that object. So let's figure out the Q of the water. The Q of the water is equal to MC delta T for the water. All right, Q of the water. Let's look at the problem. The mass of the water is 175 grams. That's just reading right through. Now the specific heat of water is 4.184 joules divided by grams times degrees Celsius. Now that's a number in your book. It's listed on in bold type on page 53. All right, that's on page 53. You're going to use it so much you'll have it memorized. However, it'll be given to you on the test. And then we need the final temperature of the water and the initial temperature of the water. Well, the final temperature of the water, it's in the problem, it's 27.1 degrees C. And the initial temperature of the water, so delta T, remember delta T is T final minus T initial. The initial temperature of the water is 25.3 degrees C. So that is a total delta T of 1.8 degrees C. So I just kind of did that in my head. So it's easier if you just make it into one number. So Q of the water, we're just going to multiply all this out, is 175 times 4.184 times 1.8. So that's 1,317.96 joules. Okay, so we're going to plug that in right here. Minus Q of the object is equal to 1317.96 joules. So if I multiply both sides by -1, that gets rid of the negative. So Q of the object is negative 1317.96 joules. And then I'm going to set that equal to MC delta T for the object. Remember this? The MC delta T up here was for the water. Right? This is for the object. So I'd have negative 1317.96 joules is equal to, what's the mass of the object? Now it's not 175 grams, that was the water. It's 54.3 grams. We don't know the specific heat, that's what we're solving for. The final temperature of the water and the object and everything, the final temperature of the water is 27.1 degrees. It's also, so the final temperature is the same for everything. It's the same for the water, the object, and the calorimeter. They all equalize to the same temperature. But what's the initial temperature of the object? It's not the initial temperature of the water. It was really hot. And if you look, it's 100 degrees C. It makes sense that the object would have a negative delta T because the object's cooling off in the water. Remember, it goes psh. When you splash it in, it cools down. So that's negative 72.9. If you take 27.1 minus 100, that's negative 72.9 degrees C. Okay, solving for C, remember we're going to pull these two numbers underneath negative 1317.96. Okay, so it'd be 54.3 and negative 72.9 degrees C. Now I know I've done the algebra right because my unit's going to be joules over grams times degrees Celsius. Also, C is never negative. It's never negative. And a negative over a negative will cancel out the negatives. All right, so we've got, I'm not even going to put negatives in the calculator because I know they cancel out this time. So 1317.96 divided by left parenthesis 54.3 times 72.9 right parenthesis. All right, that gives me 0.33. All right, and if we go 3, that would be 0.333. It looks like we need to go 3 decimal places. Joules over grams times degrees Celsius. That actually makes sense. A piece of metal will have a low specific heat like that. Okay, so for the homework, you don't actually have a calorimeter problem in it. I just wanted you to get used to calorimetry. The homework would be the review questions, page 67, 9 and 10, and practice problems, page 68. You can do 5 through 8. Now let's look at those practice problems, see if you need a hint or two on them. All right, let's take a look at these real quick, so hopefully you can see that. All right, so 5, how many joules? That's just a Q equals MC delta T, so you're solving for Q. Number 6, this one you're solving for specific heat. We did a problem like that. Q equals MC delta T, just solve for C. You'll have to do a conversion there. All right, number 7, what's its new temperature? So you're solving for the final temperature on number 7, so that's a Q equals MC delta T. And then on number 8, what you want to do is, let's see, how many calories. So you want to solve for Q in joules for this, okay? And remember that C for water is 4.184. So solve for Q in joules and then convert it to calories like you did in number 4 on the previous homework. All right, so that does it for this lecture. Go ahead and remind you, if you don't mind, to like, comment, and subscribe. And you can support the channel with the link in description box. I like to play a little bit of guitar music as my outro. So if you're interested in listening to that, here you go.